Hello, this is Jeffrey Fox. We're in the Big Data Open Source Software and Projects course in the data science curriculum. This is me here, and we're on the unit, which is Big Data Applications and Generalizing Their Structure, and we're on the fifth of the five lessons within this unit. So now we're continuing the discussion of what I introduced as the facets, because we're trying to abstract the structure or the pattern of big data applications. And I said there is no one dimension in which we can classify it. There are several different dimensions, and we use as an excuse for this that if we looked at the best respected of the way parallel computing was classified, that also had implicitly several dimensions of the classification. We call these dimensions facets, and we call the overall thing the ogres. And here we have the data source and the data style facet. And that's the first part of this is given here. It discusses all sorts of aspects of the data source and style. The most obvious one for the cloud revolution is whether you use SQL or NoSQL, a relatively controversial discussion. NoSQL has itself 5 different types: document, column, key value, graph, triple store. And of course, SQL has different implementations and different trade-offs and parallelism and non-parallelism and so on. We also have SQL on NoSQL. We went through that in some detail when we went through the discussion of the features of applications. We also discussed in that thing, enterprise data system, where we have things like warehouses, which are very important, and they illustrate that in enterprise, some pretty sophisticated data environments have been built. We had from Bob Marcus, who led the NIST effort, 10 examples of data systems, mainly effectively enterprise data systems, which use SQL, NoSQL, warehouses, and non-warehouses, and so on. Actually, most of science uses files, and those typically are managed in technologies like iRods is a sort of dominant entry here. It had an important role in the use cases led by the University of North Carolina, and we tend not to use the more sophisticated, possibly more sophisticated methodologies in the enterprise world. Under files, we have, so as well as files, we have object stores, we have blobs, which are essentially object stores, and we also have the important data parallel storage model. In the data parallel storage model, you divide the data up into parts and place different parts of the data on each node, and typically those are the same nodes that do your computing. So data parallel storage satisfies the dream/goal of bringing the computing to the data. Whereas for object stores and files, Lustre, for instance, a big shared file system as is NSF, Andrew, and things like that, those Lustre file system is typically separate from the computing cluster, and that's also true with object stores. If you go to Amazon and use S3, S3 uses different computers from the computers doing the map, say, of Hadoop. Now, we've already discussed the Internet of Things in this unit, and we've already pointed out that 24 to 50 billion devices, and they are very different sources of data from sort of a giant warehouse. There are lots of little things. The streaming, lots of data streams. We pointed out most of the use cases were effectively streaming. That corresponds to the importance of incremental updates of data sets. This is inspiring computer science to come up with great new algorithms. That's actually industry/computer science. And you need to do this in real time. G7 is the computational giant corresponding to alignment, which is typical for streaming, because when you do streaming, you're aligning the current stream value with all previous values. So alignment is closely connected to streaming. We pointed out that we have a few HPC simulations, like for climate or for computational fluids, and we need to or molecular dynamics, and we need to analyze those simulations to understand what's involved. Because the simulation the human eye is very good, so visualizations are a very good way of summarizing simulations. But sometimes, as these simulations get bigger and bigger, you have to have some way of doing what the astronomers do, finding the important events and identifying them. We've already stressed for some of the application areas the importance of geographical information systems. Anything connected to the Earth tends to use those systems. And actually, there are closely related systems, say, for pathology, because that's also spatial. Images are spatial, so you get a similar type of management environment. The next set of data source and styles highlights other aspects. The first aspect here is what we pointed out was critical for a lot of scientific data, that we needed to do things in batches. And that batches block the data, and you did not stream individual tweets, as you at least in the simplest model do for Twitter, but rather you sat there gathering data for a month and then brought a month's worth of data and added it. You get similar things with genomics, where you may have a somewhat different time scale. Your sequencer runs for a day, and then you update a day or two, and then you update with with that information. We also have various styles, so shared storage, dedicated, permanent, transient. Shared is pretty important and not so easy to see how to do, say, for the data parallel case. If you're doing the computing comes to the data, but then you have lots of shared data, and then it's not so clear how you can do the computing. So when one person owns all the data and does all the computing, it's a little easier to see how to do this than in the case where science, or universities, where you have whole communities, lots of different communities share the same disk system, and within the community, lots of different scientists share that data. And we also have, in any different analysis, we have the variety problem, that you have lots of different data, and these data come from different sources, and maybe there's some biology data and some environmental data, and the biology data stored in place X, and the environmental data stored in place Y, and you need somehow to bring them together. So now we go on to the analytics facet of the OGRES, which is the last of the facets, and these are the kernels. These are actually a little like the NAS parallel benchmark, but applied to data. Now we come to the final set of facets, which are very much like the NAS parallel benchmarks. The actual analytics, they're divided into the way we classified MapReduce into its 4 types, starting with map only. That's the pleasingly parallel case, where we saw local machine learning, which is sort of unrestricted. You can sort of run any algorithm locally because it's not constrained by the computer architecture or the parallelization. The next thing is the classic MapReduce, which starts off with search and query and index. So that's the classic web search or search of anything, which typically fits MapReduce, because you do the map is the search of the data stored on a particular node, and the reduce is the concatenation of the search results. We saw the same structure when we were summarizing statistics. That was the G1 computational giant, illustrated by the Large Hadron Collider data analysis. We have the recommender systems, which are of that type, because you define nearest neighbors and things like that for the kth nearest neighbor algorithm. That's a MapReduce application, and various simple classification algorithms. Then we have what was highlighted in the computational giant G7 alignment, which we noticed was pretty similar to streaming, because alignment takes one item and looks at, compares it with all the others, and that's typically that one item is streamed in. We have BLAST for genomic alignment and various classification algorithms which are incremental. Then we have what's the global analytics, and we have that we can look at from many different points of view. The source of the analytics. Here we have G5 and G6 and the computational giant classification. Stochastic gradient descent is used in deep learning. I use Levenberg-McQuarrie solvers, and lots of these global optimization use some variant of Newton's method. SGD does not. It's using just steepest descent. Newton's method is typically when you look at the second order approximation as well. And there's where Levenberg-McQuarrie comes in. So here's a class of algorithms which are really, to me, very exciting, and I do lots of work on them. They typically use linear algebra as their core of various types, either full matrix algorithms done by classic methods or by iterative methods like conjugate gradient. We have outlier detection. Really, clustering should go here. It's nearer mixture models than outlier detection. We have latent Dirichlet allocation here, mixture models, PLSI. These are all closely related algorithms which are chopping data up into groups, or a slightly similar idea of finding the latent factors, the hidden topics, or the hidden features which are obscured in the overall, one level down from the overall data. We have classification algorithms like support vector machines and logistic regression. We have PageRank, which is a matrix eigenvalue problem, singular value decomposition, a classic matrix algebra. Multidimensional scaling is an area we do lots of work on in my group. It's good for visualization. Deep learning is, already mentioned that, as matrix multiplication. And hidden Markov models are an important global machine learning problem. So here, the next set is graphs, and we have ones that are suitable for giraffe, which is various graph structure algorithms. These are ones where we know how to do distributed memory parallel algorithms communities, which are essentially the same as clustering. Finding motifs and subgraphs, similar to Gaussian models and things like that. Graph diameter, maximum cliques, connected components. In this category, we also put epidemiology, which is network dynamics, simulating graph algorithms, simulating systems defined by graphs. Here we have some of the graph algorithms which were not so clear, can be done well on distributed memory machine. More work is needed. I put here linear and quadratic programming, branch and bound, and things like that. And we have graph structure problems here, and which are not so different from those here, but they're ones where we don't know great distributed memory algorithms yet. And finally, we come to the overall lessons and insights from this whole 5-lesson unit. We propose the classification of big data applications, and we put in features and kernels for the analytics. That's what we just went through. And we added various other ogres we expect to add them for workflow and data systems and so on. We looked at the image-based and the streaming big data problems. We noted that these areas do not yet have high-performance libraries familiar from HPC. We mentioned there's some important challenges with order n² problems, and we are particularly excited by global machine learning. But probably up here is the key to this unit. We're trying to classify big data applications so that we can, when you build your machine or do something like that, you know what you have to look at to see whether it can be used for big data, because you know that big data's problems fall into these various classes with these various features, and you just test one problem from each class or one problem with each of the features. And that's the key idea of these this analysis. That's the end of this unit. And thank you very much. This is Jeffrey Fox signing off. Thank you.